Okay, homework 3.1, let's take some derivatives. So if we take the derivative of this function, well, first we pull out our constant, 1.4, then the derivative of t to the fifth is 5t to the fourth. When I multiply 5 times 1.4, I get 7. Negative 2.5t squared, I pull out the 2.5, then the derivative of t squared is 2t, so 2 times 2.5 gives me 5, and the derivative of a constant is always 0. So this would be our derivative. For number 10, if you're asked to take the derivative of this, you must change the form. It's a theme that has gone throughout this course and much of mathematics. So when you multiply it out, you would get this. So now really I'm taking the derivative of this function, pull out the 3, derivative of u squared is just 2u, so that's where the 6u comes from. Pull out our 5, and the derivative of u is 1, so that's where this comes from. But the derivative constant is 0, so we just don't write it down. So the derivative of our original function is just that. For 12, if I have c times y to the negative 6, I can pull out my c and then take the derivative. But the derivative of y to the negative 6th, we pull down the constant and subtract 1 from the exponent. Pull down the exponent, subtract 1 from it. So we get negative 6c, but y to the negative 7, I remove my negative exponents and write it as negative 6c divided by y to the 7th. Then if you ask me to take the derivative of this, I change the form. I do not have a radical derivative tool, so I rewrite it as t to the 1/4 would be the same as the 4th root. So now I'm taking the derivative of that function. So derivative of t to the 1/4 is bring down the 1/4 and then subtract 1 from the exponent of 1/4 and you get negative 3/4. But this negative exponent must be put in the bottom. So that's the first part of our answer. Then negative 4e to the t, you pull out a constant negative 4, and the derivative of e to the t is just e to the t. So that would be the derivative of our function. 22, if you ask me to take the derivative of this, again, I just changed the form. First start off by rewriting any radical in terms of an exponent. But then, if you have two things added together over a denominator, you can break it up and put this one over the denominator and this one over the denominator. But then guess what? If you have common bases, if you have like bases, you subtract the exponents. So these like bases of 1 and 2 give us a negative 1. So now, instead of taking the derivative of that, I will take the derivative of that. This is an equivalent form. It just is easier to differentiate. So derivative of x to a power is pull down the power and then subtract 1. But in this case, 1 is negative 2 seconds. So this minus 1 is negative 5 seconds. And then x to the negative 1, you pull down the negative 1, then subtract 1 from this exponent to get negative 2. So that's my answer, but I must remove all of the negative exponents. So this goes into the bottom, and this also goes into the denominator. So that is my derivative. Next, we just need to carefully rewrite. So if I have the square root of 5t, that's just root 5 root t. So I change that. But then root t is just t to the 1/2. And then the t on the bottom is t to the negative 1. So this is a nice function I can differentiate. So its derivative, well, for this, I just pull out the constant, but then the derivative of t to the 1/2 is 1/2 t to the negative 1/2. Pull out the constant of the square root of 7, and the derivative of t to the negative 1 is negative t to the negative 2nd. So that's my answer, but we must remove all of our negative exponents. This goes into the denominator, and this goes into the denominator. Again, notice this is not raised to the negative 2nd, so it stays in the numerator. So that would be our answer. This one is good, 26, because it really puts in contrast the difference between e to a number and a number raised to a constant. So a constant raised to a power or a variable raised to a constant. What's the difference? Well, e to a variable, its derivative is just e that variable. But if you have a variable to a constant, its derivative is take down this constant, raise it to the constant minus 1. So that would be the derivative of our original function. 28, if we have this, again, hopefully you've seen this theme. We're changing the form. So if I have a big fraction, I can break it up into 1 divided by the denominator, the next piece divided by the denominator, and that last term divided by the denominator. But then this z to the negative second can be brought up here. Z to the second becomes z to the negative second. But then z to the 1 divided by z squared is just z to the negative 1. And then these cancel out and just give me c. So now I'm ready to take a derivative. So for this, again, a, b, and c are just constants. So I pull out this constant and take the derivative of this. Well, I get negative 2z to the negative third. If I pull out the constant b, and take the derivative of z to the negative 1, I guess I get negative z to the negative second. And then the derivative of a constant is 0. So that would be my answer, but I must remove all negative exponents. And so this goes in the denominator, but this stays up top because it is not raised to a power. Only the stuff that's raised to the negative goes back in the denominator. This is negative b, so it chills there because z to the negative second, that must get moved to the denominator. Then 40, it gives us this equation and says find the equation of the tangent line to that curve at this point. So since it wants a tangent line, I automatically write down this equation, y minus y1 is equal to mx minus x1. Since they want to be tangent at this point, so my curve looks something like, well, let's see what it looks like, x squared of x. So let's see what Desmos tells us it looks like. So if I go x plus the square root of x, something like this. Let me make sure it's plus. Oh, it's minus x minus the square root of x. Ooh, it's really pretty. It looks like this. So that's what our graph looks like. So I'm going to go kablamo. And then I'm going to go right, and go done, save, and I'm going to put it over here because I really think these representations, other ways of looking at it, really help us. So there's my graph, and I'm going to think about that graph as I do my work. Boop. Okay, so what we're trying to find is the equation of the tangent line at the point 1, 0. So there it is, 1, 0. I'm trying to find the equation of that line. Well, I know that one point on the tangent line is that point that it is tangent to, 1, 0. So I can plug in my x1 and y1. It's just 1, 0. So now the only thing I have to do is find the slope of my tangent line. But the slope is just my derivative at this x coordinate. But since this is 1, 0, I need to find my derivative, or slope of the tangent line, at 1. So my function is just x minus x to the 1/2 because I change my root to a 1/2. And so when you take the derivative of x is 1 and derivative of x to the 1/2 is 1/2 x to the negative 1/2, which I can just simply write as 1 over 2 square roots of x. So if this is my derivative, then if I plug in 1, I get 1/2. So that means my slope is just 1/2 for my tangent line. So I put in my 1/2 right here, and that is the equation of my tangent line. If you want it to look nice, you can distribute the 1/2 and get this. So the line that is tangent to my curve at the point 1, 0 is just 1/2 x minus 1/2. And we're done. Oh, no, we got 50. Okay, so 50, it says this is position, and it says to find acceleration. Well, the first derivative is velocity, so my derivative of t to the fourth is 4t cubed. The derivative of 2t cubed, well, I do 2 times t to the third, but the derivative of t to the third is 3t squared, so that 2 times 3 gives me 6t squared. The derivative of t squared is just my 2t, and the derivative of t is 1. So that's my velocity, but then the change in the change is my acceleration. And so I pull out my 4, the derivative of t cubed is going to be 3t squared, so that 4 times 3 is where I get this 12. Pull out a constant 6, the derivative of t squared is 2t, so that's where I get 12t. Pull out a constant 2, but the derivative of t is just 1, so that's where that comes from. And the derivative of a constant is 0. So there is my acceleration. But then they want to know the acceleration after 1 second. You just plug in 1 and get 2, and the units for acceleration are meters per second squared. Why? Because for position, it's meters. For velocity, it's the change in meters every second, change in position over time. But then if I say, how does that change with respect to time, that's where you get meters divided by second squared. That's where you get meters per second squared, because it's change in meters per second every second. Your velocity is changing every second. That's why it's meters per second squared. Great work.